Hello everybody, good morning. How are you? Awake? Yes, nice. So, welcome. I'm Alex Casalboni, and today during this session I'm going to tell you about a few different concepts, so in one title, a lot, right? So, data analytics, serverless, columnar formats, a lot of different topics. 2 words about myself. I'm a software engineer, I'm a web developer. I've been doing data science and development for the last 8-9 years, and I've been an AWS customer before I joined AWS for more than 5 years. So, but enough about me. I want to ask you what you guys do. How many of you have ever used or created or maintained a data warehouse in your life? A few. Great. And how many of you have heard serverless before as a concept? Everybody. Awesome. So today we're not going a lot into serverless itself, into AWS Lambda or like the function as a service specifics, but we're going to see how you can apply the same concepts to data analysis. For example, we are going to see how you run SQL statements and queries without managing a cluster, without managing a database, without having to think about serverless. So similar approach, different use case, right? So what's the agenda? I want to tell you about some of the data challenges that we've been facing and how they have changed in the last few years. How columnar formats and why they matter, what they are, what does it mean for us as a developer or a data analyst or data engineer, however you want to call yourself. A little bit about data lakes and data warehouses. Okay, data warehouses. How many of you have used or created a data lake? Okay, a little less. Cool. So they're not too different. They are not, replacing one another. So let's see how we can use them together to extend one another. And then what is this thing of serverless analytics? And then I want to skip all the theory and show you a real demo how we run this stuff on AWS. Okay, data challenges. There are a few things that changed in the last few years. We are used to having data that came maybe from a single source or maybe from a couple of sources, and maybe there was 1, 2, 3 analysts or data people that were just looking at it, and nobody else cared, or nobody else wanted to dive deep, or nobody else think they could at all. So 2 big things that changed. One is the variety, meaning how many different types of data that might be coming into your system, and the volume. So how much, if you measure how many megabytes or gigabytes or petabytes are now being stored in your data warehouse or your data lake. And that's been changed in the last few years, because now you have documents, unstructured documents, semi-structured documents, very structured, maybe relational or not relational. You have all sort of different kinds of data that you may want to combine. And a very new trend that's been more and more popular has been also the real-time kind of data, which is kind of different if you think about it. It's not the usual typical traditional data that you can design in advance and that you can carefully define a schema in advance. It's been changed how you think about this stuff and how quickly people expect to be able to store new data. If it takes more than a day or 2 for you to define a new data type and start collecting it, you're probably doing it wrong. You need to collect insights in days, not weeks or months anymore. So the expectation has changed, not the technology. And the second big factor that changed is how many different kind of consumers you can have today as a data warehouse or as a data platform. So it's not just a data scientist or the business analyst anymore. You might have other analytical platforms. You might have complex dashboards. You might have people that want just to do data exploration and data visualization on your unstructured or structured data. Or even applications that need to fetch the data to do machine learning or to build models or just to build their own third-party monitoring or reporting solutions. So these 2 have changed a lot. how much data and what types and who is consuming it. And the challenge is that you still want to be able to do all sorts of things like ingesting and discovering and building catalogs and understanding and curating. So it's not easy when you start having all these different data sources and consumers, because the ultimate goal is to find insights. So we wouldn't really store billions of records and petabytes of data if the ultimate goal wouldn't be finding useful information in there. That's the whole point. Either you're using it to build machine learning models, and then you need a lot of data about your users, your customers, how they use the product, or you want to go and analyze it, build dashboards. That's more or less the 2 or 3 goals that you might have. And we're not talking about small scale data. Okay, I will say big data a lot today, bear with me, I know it's a buzzword. But we're talking big data for real. Like there are customers like FINRA, for example, that's now managing like 99% of equities in the United States. They are ingesting more than 20 petabytes of data in their data warehouse. And it's not a startup, it's not a consumer product, it's a financial institution. So kind of large, big data use case with real financial institution regulations and constraints. So this is the kind of scale that we're talking about nowadays. It's not a few gigabytes anymore, it's not a few hundred gigabytes, it's petabytes, and they are planning to go beyond that to the exabyte scale. So that's where we are moving as a market. We have also been used to having one big database for everything, like one database that fits all your use cases, but that's not really the strategy anymore. At least that's not how Amazon Web Services sees this, and that's why we've been building purpose-built databases, because you just need to choose the right tool for the right job. You need a real-time databases with subscription, cool, or you need a high throughput data ingestion for 2,000 million queries per second, writes per second, cool, that's another database. You need graph databases, you need NoSQL or SQL relational databases. So there are different flavors for different problems, for different skill sets. And we really believe in this. And that's why you find all these sort of databases. Let me show you a few. So there are actually 3 phases when you go and store and collect and analyze data. Of course, you have to start with the collect phase, right? So up here you find some of the services that allow you. We're talking about managed services usually. So, for example, Kinesis Firos is the service that allows you to ingest all your data, act as a buffer, and compress it, encrypt it, and just put it into either Amazon S3, our object storage, or Elasticsearch if you have search, if you need to support search capabilities. But there are a lot of different ways to ingest your data into the cloud. So if like Kinesis, the Kinesis family doesn't help you because you already have a petabyte of data, you might even want to use Direct Connect to connect your on-prem architecture infrastructure to the cloud and just put it and just start transferring your data. But if it's really not enough and you need to do it quickly, that's what most people do, we can even ship to you a physical device and you put your data in with the optical fiber and everything, and then we just ship it back. That might be even faster to bring your data to the cloud. So there are different options to bring your data in there, but once it's there, you need to choose where to store it. So that only depends on, okay, either how much it is, how much data it is, or what data it is. So it might be unstructured data, it might be images, it might be binary files, it might be CSVs and JSON and all sort of semi-structured or unstructured data. So you may want to put it on S3. Maybe you don't need to use it, all of the data every day, all the time. So maybe some of it can actually go and maybe be stored on an archiving service like Amazon Glacier. So it's much cheaper for you. You don't have to really access it every day. If you need it, you can go and access it in a couple of hours, 4 or 5 hours. If you don't need it, why shouldn't you pay 10 times less, right? Or maybe you have relational data. So relational database service, RDS, is already supporting like I don't know how many, like MariaDB, MySQL, PostgreSQL, Oracle, SQL Server, like all possible SQL relation databases. And then you have all sort of NoSQL variations of this, such as DynamoDB. That's how you store your items, not records, because there is no real schema. Or maybe you need to support search in your application, or you want to build dashboard based on text, full text search or stuff like that. So maybe you want to use Elasticsearch or Cloud Search, which is our Elasticsearch managed version in the cloud. Okay, data is stored somewhere. Now we need to do something with it. So maybe you want to plug in services such as EMR, Elastic MapReduce. Maybe you are a Hadoop user developer, so you're comfortable with building your Hadoop cluster on EMR. Or maybe you don't want to do that. Maybe you want to use other managed services such as Kinesis Analytics that will kind of connect to your Kinesis firehose or Kinesis streams to do real-time analytics. That's what Kinesis does. Or maybe you want to go into the more traditional data warehouse services like Amazon Redshift. That's a large-scale traditional data warehouse service. Or the new cool ones that I have a t-shirt, Amazon Athena. That's what we are going to see mostly today. That's how you do serverless SQL on top of your data lake. Very cool service. But these are tools to build queries or to kind of extract and aggregate and manipulate your data. How do you visualize this stuff? So you may want to use tools such as Amazon QuickSight for data exploration, data visualization. If you have data but you cannot kind of explore it and visualize it and play with it and discover it, it's useless data. So not all data is really easy to visualize and put into a database. That's why you may want to use some other services from the AI, artificial intelligence suite, maybe to convert audio into text, or vice versa, maybe text into audio, or maybe to extract insights from text with Amazon Comprehend, so it can do natural language understanding. Or maybe you want to detect faces from an image, or you do all this sort of AI tasks that you don't want to rebuild yourself. So maybe as part of your data ingestion, data collection pipeline, you want to have an AI step to do some data transformation before you store it in your data warehouse or data lake. So these are the three different phases. There are actually a couple of services down here that are out or between these phases. So one is the data migration service that kind of helps you to map your data between one data source and another, or help you ingest data from other external data sources. And AWS Glue, which we'll see in a minute, helps you build a data catalog and discover your data with crawlers and automatic discovery. So this is more or less the picture. Let's now dive deep into some of these services. But first, I want a quick parenthesis about columnar data. How many of you have used or seen column data before? A lot. Awesome. Do you like it? Did you enjoy the experience? It's a different mindset. So there are different open source standards in this space, like Parquet or ORC. And the point why they were invented in the first place is that we need a way to optimize the performance and efficiency and even the cost sometimes, which is kind of related, of analytical queries. So the traditional database that you have in production for your service, for your product, it's optimized maybe to query a specific user or to query a specific product, to do joins and to serve one specific user at a time. So those queries are record-based. You probably want to retrieve one or a set of records. While analytical queries, most of the time, work on aggregates and big chunk of records that you don't really need to do where user ID is 5 kind of queries. You don't care about that. Usually you want to extract information, high-level overall information. So those queries are a different beast to optimize. That's why sometimes we need to change the format of our data to optimize how you access and manipulate it. Very intuitive, very intuitively. So that's more or less how a row layout looks like. So in a typical traditional databases, here you have So if we have records like A1, B1, C1 is record, because A, B, C are 3 fields. So we have a record in every line. So that's usually how you store in the raw layout. So you have one record, A1, B1, C1, and then another record, A2, B2, C2, and you store a record after another, because most of the time you want to access records, individual records. So in the columnar layout, we do completely the opposite. It's intuitively simple. So we store the first column, all the A column at first, and then we store the B column, and then the C column, and so on. So probably not in a big, huge file. Maybe you want to have chunks, so maybe you want to have multiple, maybe several hundred files, depending on how much data you have, how many records, and how many columns you have. The interesting detail that you need to be aware of is that at the beginning of each section, you also have some metadata about that column, such as how many records are there, or they maybe are already sorted. So it's useful for you to do kind of sorted queries as well. Or if you think about it, if you do average of a field. How much data you need to read here and how much data you need to read and access here. If I need the average of column A, I don't need to read the rest of the 2/3 of the file. I can just read that. If it's not already in the metadata, that might be, I will just go and read 1/3 of the data set instead of 100% of the data set. So it helps us with those kind of use cases. Well, why it matters? Big data, again, we have petabytes or exabytes of data. We want to make sure our queries run in seconds or minutes, not hours or days, which is the case if you use more traditional data formats and databases. Another cool use case is the real time. Again, we want to make sure that we can extract information from data coming in real time. Think IoT, think click streams, think anything that happens right now and that you need to be aware of it 1 minute later, 2 minutes later, not 20 hours later. Okay, real-time information to take decision for your product, for your company, your startup, whatever. Third, interesting why it matters is data exploration and data visualization. We want to have tools that allows us to do interactive data exploration. Okay, we don't want to be stuck with static dashboards that we cannot dynamically change and dive deep into a specific area or part of the data. So by having 10 times faster queries, we can allow this kind of dynamic data exploration use cases. Otherwise, you're stuck with static images, which is not what we want as data analysts or engineers. And well, have you ever printed a long query? This is as long as it can get. It's not fun. Some of these queries are particularly hard to debug or even to understand or to read. Never print a long query. It doesn't make you feel better. Thing is, this query probably runs in weeks. You don't want to even know who wrote it. Maybe it was auto-generated by some kind of tools. I don't want to know, honestly. Thing is, I will keep saying big data, guys. I'm sorry. That's the big reason why we're here today. And some people will tell you it's not about how much data you have, it's how you use it. That's fine. That's true for some use cases. If you're doing machine learning or deep learning, or if your analysis needs to reason on a small data set, that's totally fine. But there are use cases like FINRA and like Netflix and like Twilio and like customers that are global and that have a lot of data, and they need a way to do this sort of analytics in the same way, in the same few seconds or few minutes instead of hours and months. Otherwise, they wouldn't be as fast as and innovative as they are. So that's why we are here. So sorry if I keep saying big data. Little parenthesis. Let me tell you how traditional data warehouse used to work. Maybe you have done it yourself. Typically, I'm not saying this is the rule, but typically you have relational data. So you need to define your schema in advance. If you need to, at some point, start storing new data, collecting new data, you need to sit there, talk to the developers, agree on some data format, data schema, data types, and all those things. and creating the table, agreeing on everything is tough. I've done it. I'm sure you've done it. And then what typically happens is that you build ad hoc queries, ad hoc, and your reporting, your operations were really ad hoc. There's a lot of operational heavy lifting, as we call it. It's not fun. And the scale that you can reach with these tools, with these traditional data warehouses, is fine. They were designed 10, 20 years ago, so the scale you can get is the giga, tera, maybe petabyte if they are really, really good. But we want to do more. We want to do exa scale. So when you need to order one, 2, or 3 orders of magnitude, sometimes you need to change your tools. That's why the concept of data lake became popular. You may have heard it. It's another buzzword of this talk. I'm sorry. Typically, with the data lake, you can think of it as an extension, not as a replacement. So if you see here, maybe you have a data catalog, and you might want to have both a data warehouse and a data lake. I'm not saying, hey, just throw your data warehouse in the trash and start building a data lake. You want to have both. They have different goals, simply put. And what's the difference? Usually you have relational and non-relational and possibly even completely unstructured data, because if you remember, we now want to store any sort of data, maybe data coming from social media, data coming from our applications, our systems, logs, our people uploading CSVs. So we want to be able to handle any sort of data from any data source. The schema is typically not defined during data collection, not even during data storing phase. You usually define the schema when you go and analyze the data. So it's like a mental shift. Okay, first collect it, store it somewhere. Then when it's there, and when you've done data discovery, built a data catalog, you can go and analyze it by defining the schema afterwards, which is a different way to do it. We'll see how. Well, the good news is that it still allows you to build, to gain insights, to analyze your data. There is a different engine under the hood. Maybe you have heard of Presto. Today we are using Amazon Athena, which is built on top of Presto. So that's how we are going to access our data. And even the cost of storage and analytics is very convenient, because under the hood, you have the possibility here to completely separate storage and compute. Okay, we have stored our data somewhere which is not a database. Maybe it's an object in a distributed object storage, such as Amazon S3, and the storage is there. And now we want to add some sort of computing capabilities and analytical capabilities on top of it. But if you think about it, it's completely separated. There is no situation in which, hey, the instance storage is low, we need to change instance type, and maybe, oh, we also need to increment the monthly cost because it comes with more CPU and blah, blah, blah. So here, that doesn't happen. Storage cost is there based on how much data you put in, and the compute cost is completely unrelated and independent. If you don't do any query, you have no computing cost. That's the big difference. And also, since the compute cost is separated, it also means that a cloud provider, such as AWS, can make it completely transparent to you. So you don't even see the machines, you don't even see the cluster, which means that we take care of parallelizing all the workload for you. So that's another advantage. Your query will run faster, because you don't have a 5-machine cluster that you're maintaining. You don't care. If we can parallelize the query to 200 machines, we'll do that. We already have a cluster down there running. You're just not seeing it. That's exactly what it looks like. So you may want to have data on S3. There is AWS Glue that helps you build a catalog. And all of this is powered by the AWS network and all the, like Snowball, the device, Snowmobile. Snowmobile is actually a big truck that will come to your data center, and you can put data in it. It's like, I can't remember how many petabytes of data you can put in. If you petabytes of data on-prem, call us, we'll send some trucks. Well, all the benefits of S3. Durability, I don't know how many nines, probably 11 nines of durability and availability. Security is there. You have all the tools to make sure that your data on S3 is secure, meaning only certain users or certain services or certain roles can access the data. So you have very fine-grained access on the up to the object, specific object or folder or bucket. That's the kind of compute and storage cost we are talking about. So that's a gigabyte, 2 cents, 2.3 cents, and that's the cost of a query, 5 cents per gigabyte. So if your query is scanning 500 megabytes of data, it will be 1/10, it will be 0.5 cents. And this is a mental shift again. We are used to having a monthly cost for your data warehouse, our infrastructure, whatever. And you can run any number of queries on it. The cost is the same, but it's slow. Here, you have always fast queries, but you pay by the amount of data that your queries are scanning. So it's a different mindset. These are some of the components. Again, S3 is at the very center. It's the father of every AWS service. If you need storage, it's probably S3. Data ingestion phase, we already mentioned kinesis. There is some ETL that you may want to have to convert data, manipulate data, clean, filter, whatever you need to do with the data. You have the catalog with Glue. You might maybe have some data on Dynamo if you want to build indexes or very fast kind of data fetching, maybe to understand where the data is. Elasticsearch if you need to do search. We already mentioned that. How do you access this data? So IAM, Identity and Access Management Service, will help you with the fine-grained policies to understand who can access what. Cognito, same. It will grant your clients, maybe a mobile or a web client, temporary credentials to access the data, if you will. API Gateway, Amazon API Gateway is a RESTful interface on top of literally anything. So it could be on top of your AWS Lambda functions that may go and read data, or on top of your on-premise services if they are connected to a VPC. You can do everything with API Gateway. So if you need to have RESTful access to your data, you can do that as well. And then all the analytical tools. It could be QuickSight, we're going to see that in a minute. It could be Athena, Elasticsearch, Kinesis, RDS, Redshift, EMR, everything. You can just read data from S3 from any other service. It's built in. I want to stress the point that all of this is serverless, another buzzword, I'm sorry. Serverless because you don't care, you don't see the servers anymore. There's no cluster, you just run the query and it will run it for you. You don't care about the infrastructure, you don't pay for the infrastructure if you run 0 queries. That's the power. No, never pay for idle, we say. And it will scale up to infinite and down to 0. That's another advantage. If you already have a Redshift cluster, though, you may want to use like a hybrid kind of thing, which is the perfect hybrid between Amazon Athena and Amazon Redshift. So Redshift is traditional data warehouse. Athena is completely schema on read based on the data on S3. Spectrum is a solution in between where you still have a Redshift cluster and some of the data in Redshift is there. Some of the data of your Redshift tables are on S3, and you can kind of combine and join and merge these 2 different data sources. So very powerful. There is another problem with all of this big data thing. It's that the more you go into the big data world, the amount of dark data, which is the amount of data that you have no idea what it is, goes up. Okay, it's exponentially, almost exponentially. And you don't want that. You want to have all the tools and the data discovery capabilities and data crawling and exploration capabilities so that this dark data stays as low as possible. Because dark data that you have no idea what it is useless data. You don't want that. That's why we have Glue. That's why AWS Glue will help you build a data catalog. How do you do that? Well, you see these little cute spiders? Those are crawlers or spiders that will go around your data sources and detect the schema and build virtual schemas and build new versions of the schemas if they detect that the schema has changed. This really helps you keep track of changes and understand your data and even query your data without efforts. The second advantage of Glue is that since it's able to go and crawl and catalog your data, it can help you build ETL jobs, which just means moving data around between data sources or manipulating data between data sources. So it can even auto-generate customizable code in Python or Spark or even Scala and other languages, and you can customize that code and maybe schedule it to run a couple times a day, a couple times an hour based on your needs. So very cool. And also serverless, meaning you don't even see the servers, the machines, the physical machines, you just run the job. As simple as that. So what can crawlers classify? Not just data on S3, but even data on RDS or data on Redshift or data on your relational, non-relational databases. And you can plug in your JDBC connection if you want. So you can connect to Athena as well as you can connect to RDS or to Redshift with your typical traditional tools that you're used to or libraries that you're used to. So very, very useful. So these crawlers will also help you understand if different schemas are similar. As you can see, name, ID, address, schema B, name, ID, address, it's supposed to be very similar. It's almost the same. For some specific data analytical queries, this might completely be the same data or the same schema, in fact. And that's why these crawlers will even help you understand the similarity of two schemas. They will tell you based on what we see, it's 87% similar. So you may want to combine it or run an ETL and make it 100% similar so you can query it and so on. Partitions are very useful to optimize the latency and the speed and the cost, in fact, of your queries, and being able to automatically go and find partitions in your data will save you a lot of time and will save you a lot of operational maintenance cost and time. So that's also what Amazon AWS Glue and crawlers will do for you. And when they detect that something has changed, they will automatically enable the schema versioning feature. So maybe something changed, they will tell you what fields were added or removed and at what date, and so that you can exactly know what to query if you want to have a given particular schema or not. And how do you create these kind of virtual tables? Different ways. You can do it with a UI if you're comfortable using the UI, web UI, or maybe you can write a statement, an SQL statement through Athena, or maybe you want to call a Glue API. Everything in AWS has an API, and we build web services. Or maybe you already have this stuff defined in a Hive meta store, so you may want to import it to Glue. So based on where you are, based on what you have today, different options. Quick parenthesis on Spectrum, it's, I like to say, the best of both worlds, because you have the flexibility, like the exabyte scale flexibility of a data lake with the speed and data flexibility, so you can update data as well, given by a traditional data warehouse. So you can have the best, even as far as performance. This is what it looks like, more or less. So when you have a SQL query, an SQL query, whatever driver you're using, this is the Redshift lead node, and there is the Redshift cluster up here, okay? What happens is that the leader node will understand how your data, how your query needs to be executed, and if the data is all in Redshift, it will stay there in the cluster. But if the data is on S3, it will delegate all the parallelizable computation to the Redshift Spectrum cluster, which is not managed by you, it's managed by us, and it's much, much, much larger than your traditional Redshift cluster. And once the data is being fetched from S3, maybe aggregated, and all the partial subqueries have been executed and we have the partial results, they will be given up to Redshift and the query will return to you through the leader node. So this is more or less the architecture. That's how you do data lake on S3 with using your glue catalog, using your favorite analytical solution. Today we will see Athena, and then you go and query, and visualize and build dashboards and reporting with QuickSight. Enough theory, okay, too much theory today. So let's go and do something real in practice. So I will stop mirroring, if that works. Yes. We still have 5 minutes, so I can show you something. Okay, so I've built a data ingestion pipeline. Okay, this is Cloud9. Nice, we're back. This is AWS Cloud9. It's an IDE in the cloud, but just easier to show you. So this is my template. It's a YAML template that defines my application. I have already deployed this template. It's just infrastructure as code. So I have a Lambda function to do data manipulation. I have a delivery stream. This is Kinesis Firehose. So it will take my data and put it on S3 automatically. 0 lines of code written on my side. But I have deployed it 3 times. Okay, I wanted to show you the difference. We have mentioned that if you push data as is, okay, you have your data there. If you compress it, as you can imagine, you have much fewer data. You might reach 70, 80, 90% compression rate. It means you have much less data to move around, and that might optimize your query speed and performance and costs. And then we want to see how much we gain with columnar formats as well. So I've deployed it 3 times, and I built a script to post and put the same data to the 3 delivery streams, to the 3 different stacks in here. So I've put data such as a name and an action and a value with random value. We have action charge and action refill, so there are 2 different kind of data actions. And I've done it again 3 times using 3 URLs: uncompressed, compressed, and partitions, which is actually Parquet. We'll see partitions then. Okay, that's what it looks like. So that I have 3 S3 bucket. Let me show you what it looks like. So this is, for example, the uncompressed bucket. Is it big enough? No. So in the uncompressed bucket, we have Firehose and the year and the month and the day, and then we have the hour, because that's done by default, so you can split data and query it more efficiently. And then we have hundreds of objects. Okay, all these objects will compose our table. It will be a virtual table. So this is the Athena UI. Let me zoom a little. So here we have three different tables: one for uncompressed, compressed, and Parquet. So if we preview the table, there shouldn't be much. It's probably a few megabytes of data. This is what the data looks like. We have all the records auto-generated. If I remove the limit 10, it's going to show us how much data it's in there. Okay, it's 1 megabyte. So we're not talking big data today, but the good news is if I keep pushing data up to a gigabyte or a petabyte or an exabyte, the infrastructure doesn't change. The costs do change, but my queries, I don't need to change any infrastructure at all. So we have 1.15 megabytes of data, and if I read star from the table, of course, I will scan all of it. So now I'm paying for this 1 megabyte. If I want to scan the compressed, meaning this table has been already compressed by Firehose, it will be much less data. So it will be a cheaper and faster query. So this will be 70 kilobytes. So from 1 megabyte down to 70 kilobytes. Same ratio, it will be 1 gigabyte, 70 megabytes. Kind of, that's the scale we can gain just by compressing the data. If we go with the Parquet table, if you remember, there is some metadata. That's why we have 30 kilobytes more. So the Parquet is not storing less data, it's optimizing the access to the data. That's why we have some overhead in the amount of data in total that we are storing. But let's try to run some actual queries. I have saved a few. For example, if we count our records, okay, let's count from the uncompressed one. As we are counting, we need to go and fetch everything, and so we are scanning the whole data set. So we are scanning 1.15 megabytes. If we count the compressed one, we are still scanning everything. It'll be faster because it's less data, but we are still scanning everything. If we count the Parquet, as you can imagine, it'll be much faster. It's actually scanning 0 kilobyte. Okay, so we made this query free. Why? Because the Parquet metadata is helping us. It's already in there. We need to read just the first metadata of the first column. We already know how much data, how much records are there. Let's do something more interesting. Maybe a where group by kind of query. So we want the name, the average value of the value, where the action is refill, group by name. So we can have a nice report, right? It doesn't work. Nice. And now it works. Nice UI. So we have a nice report. We can build something with it. With the uncompressed, we are still scanning everything. If we compress it, okay, you get the point. The compressed and uncompressed are always scanning all the data set because we are not optimizing anything. But if we go and do the same with the Parquet format, we are actually scanning 20 kilobytes, which is like 20% of the data set. Why? Because we are accessing only the name, filtering on the action, which is optimized as a query, and averaging the value, which might be also in the metadata. So with Parquet, we are saving, I don't know, like maybe 70% with respect to uncompressed. Let's do now something more complicated. Have you ever seen, I'm sure, queries such as this, where you have nested queries inside? So we are selecting the name and counting the number of charges and counting the number of refills, grouping by name. So we want 2 different counts for each person in our data set. And this way we are scanning the data maybe 2 or 3 times, right? Because we are doing 3 selects and we are probably scanning the data set 2 or 3 times. Let's see if it's true. From the uncompressed one, exactly. So we are scanning 3 megabytes. Okay, this means we are scanning the whole data set exactly 3 times, which is okay. We expected it, but if you have 1 gigabyte, you will scan 3 gigabytes. We can optimize that. Very similarly with the compressed one, you got the point. You can do the math. It will be probably, I don't know, 200 kilobytes. Yeah, 212 kilobytes. Let's try to do the same with Parquet. As you can imagine, it will be faster and working on fewer data. But let me show you that it's actually, it's actually scanning 60 kilobytes. So it's still the ratio between how much data you are scanning and how big is your data set. So we went from 3x to 0.5x to 50%. So Parquet format is helping a lot. I want to show you that we can do even better. I haven't mentioned yet, but with these Athena queries, we can even do ETL. Okay, we can say, hey, select value name action from the Parquet table and create a new table that we will call partitioned. Use the Parquet format, compress the Parquet with snappy compression, put the data in here, in this S3 bucket, in this S3 folder, and create 2 new partitions, one for the name and one for the action. These are the 2 partitions that we can create. It doesn't make sense to have a partition for value. It's random integers. So if we run this query, Athena will actually move data. So we are doing SQL ETL. We are moving data around. And this is not a view. This is actually moving data into another S3 location. And there we go. We have created a partitioned table. Let's try to query that. So if we want to run the same query, such as this one, but from the partition table, I would guess it's still free because it's still Parquet. So it should be scanning very little data. Actually scanning 5 kilobytes, still less. But if we now try to run this one, the one that was scanning the dataset 3 times, partitioned, partitioned. So what do you expect? It should be faster. It should scan fewer megabytes. It's actually scanning 0 kilobytes as well. So by creating these 2 partitions, we made also this query free. You're not paying whenever you run this query. That's cool. I'm not saying now it's taking 0 seconds. It's still fetching data, maybe from the metadata from Parquet, from the partitions metadata, but it is free. So cool. That's the power of Parquet, partitions, and serverless analytics. Let me show you some statistics. So simple query. From the uncompressed format, we went down 94% just by compressing. And I'm talking about cost. We went down another 70%. Oh, all right. Sorry, guys. This is very useful, huh? Okay, let me do that. Cool. So we went down another 70% with the Parquet format, and by adding partitions, I didn't show you, but we will go down another 70. Okay, so we reduced and improved for cost 99.5% down. Simple count query, very similar, 94, 100% and 100% with Parquet and partitions. So you make this kind of count queries free, basically. 100% improvement, nice. So nested query, it's not too complicated. It's not the 5-page long kind of query that we saw, but still, we got 94, 72, and down to free with partitions. So based on your data set, maybe you have multiple tables, you can achieve this kind of performance and cost improvements. Performance, we manage that. We manage that because we manage everything under the hood as far as infrastructure. So if your query can be parallelized, we will parallelize it as much as we can. You can take care of optimizing for cost. That's why I'm showing this. So once you have this, you can take your Athena queries or even your raw data and ingest it into QuickSight. So why you may want to do that? How many times it happened to you that you built a beautiful, like the best, beautiful, most beautiful dashboard of your life, but then it was offline because the data warehouse was off. It happened to me, right? So QuickSight is really interesting because it will actually ingest the result of the query into an in-memory engine, meaning you are decoupling the query engine from the data visualization engine, okay? So once all your data is ingested into QuickSight, your dashboards never go down, okay? What you can do is 2 things. You can reschedule data ingestion, like update the data source into QuickSight periodically. Every hour, fine. Every 6 hours, you decide when. Or you can say, okay, do not ingest anything into the in-memory engine. Always go back to the data source if that's what you want. If you have real-time data coming and you're constantly writing new data into S3 and you want QuickSight to be able to pick it up and show updated dashboards every time you watch it, you can also do that. But it's been optimized as an in-memory engine to not have your dashboards down ever. So I would suggest using that option. Additional resources. So when you start building this stuff, it's really useful to have some kind of data generator so you can generate hundreds of megabytes or gigabytes without actually writing a script, as I did. So follow my advice. I just did it. Use the data kinesis data generator. So it will actually spin up some infrastructure in your account. You specify the schema and it will start pushing data, hundreds of records per second if you want. So you can do all your experiment or your data analytics experiments with fake data. Still very, very useful. The code that I've shown to you today, the template and data pipeline is on GitHub. So check it out, Alex Casalboni on GitHub. If you want to read more about this stuff, we have a big data blog. as well. So check it out. That's all I had for today. If you have questions, we still have more or less a minute, so feel free to ask me anything. Thank you, guys. Any questions? Yes.
When you were showing us live the demo, we saw that the amount of data scanned was dropping, but not the execution time. Parquet was taking something like 2.7 seconds, while compressed was 0.9.
So I can tell you. So the question is, we are optimizing costs, but are we also optimizing for performance? Because it looked like it took longer. So what I didn't have time to show you is that there is some not caching, but as far as the data fetching, data exploration that Athena does and Presto under the hood does, there is some caching in between. So the first time you run a query, either Parquet partition, not compressed, there is some overhead for data discovery. So those 2 seconds that you saw was because it was the first time I did that kind of query. If I rerun it, not because it was cached the result, but because the data discovery would be cached, it will be faster. So sorry about the confusion. But yeah, good point. Any other? Yeah. Yeah. So you can use your ODBC or JDBC tools and drivers if you're comfortable, and you can map them to your Redshift or to your Athena or to, yeah, absolutely. We don't want to force you to use another tool. It doesn't make sense. Absolutely. Okay, great. We are out of time. Thank you for being here. If you have questions, I'm on Twitter or I'm here for maybe 10 minutes. Thank you.